So unigram language models make very strong statistical independence assumptions. In particular, it assumes that the probability of a token doesn't depend on the past at all. This is obviously unrealistic. We can slightly relax this assumption, which results in what's called a bigram language model, where now we assume the probability of a token only depends on the previous token. So in particular, now we make this approximation where the probability only depends on the previous token, and the fact that the notation, the random variables on the left-hand side and the right-hand side are different is deliberate. In particular, we're also making a time invariance assumption. So the random variables W are position sensitive, but with the time invariance assumption, we assume that these bigram probabilities are shared across time. So in particular, on the left-hand side, this is the probability that token at position 2 is x of 2, given that the token at position 1 is x of 1. Whereas the object on the right-hand side is the probability that token x of 2 is followed by x1 in any position. And again, this time invariance assumption enables more efficient learning because there are fewer parameters to estimate. So how many parameters are there in this bigram language model? Well, for the very first token, we still need to learn a unigram language model over at that very first position. So there are v parameters there. But for all the tokens occurring after, we now have this object that gives a probability distribution of a token being followed by any token, and then there are v squared such scalars that parameterize this next token distribution given just the previous token. So a bigram language model has v plus v squared parameters. So what is the shape and meaning of these parameters, theta? We can think of theta as now a vector of size v plus v squared, where the first v elements correspond to the unigram probabilities for the very first position. And then the next v squared elements are the conditional probabilities of any token conditioned on any token. So there are v squared possible values for these conditional probabilities. And while we won't get into derivation, it's not difficult to show that if you do maximum likelihood learning with a language model that has this bigram parameterization, each bigram probabilities are given as follows, where theta I given j is obtained by counting the number of times token I was followed by token j and dividing by the number of times token j occurred. So again, you're counting and dividing, and this is still a count-based language model. So that was a bigram language model, which relaxes unigram language model's assumption that the probability of a token at position t doesn't depend on the past. Of course, bigram language models are still unrealistic models of language. In particular, a probability distribution over the next word certainly depends more on just the previous token. So we can generalize this to n-gram language models, where the probability of a token occurring depends not just on the previous tokens, but previous n-1 tokens. And if you make the same time invariance assumption that we've been making, maximum likelihood learning of this n-gram language model is still just counting and dividing. So in particular, the scalar probability of a token I occurring after the context token j1 to jn-1 is simply again obtained by counting the number of times token I was actually followed by the context in your training set and dividing by the number of times the context occurred. And this is the empirical estimate of this conditional probability. So in principle, we can keep relaxing the statistical independence assumptions and have higher order n-gram language models that are more and more flexible and capture richness in language. But it turns out this raises an important issue. And we can see this issue even with a simple bigram language model. So again, in a bigram language model, the probabilities or the learnable parameters are given by a vector or a set of v plus v squared numbers, where the first v elements are the probabilities for the very first position, and the next v squared elements are the probability values for a token being followed by any possible previous token. That means one of the probability values in this conditional probability distribution is a scalar for something like the probability of a word ziziva being followed by that same word ziziva. Now, both are incredibly rare words, and for example, if you do a Google search for how many times this actually occurred, it basically occurs 0 times. So that means the probability that you assign to this conditional probability, in particular the probability of ziziva being followed by ziziba, the empirical probability with a count-based language model is 0. And we can see how this sparsity issue, i.e. some n-grams just never occurring, becomes worse and worse as we consider higher order n-grams. So that means a lot of the probability values that we're going to estimate are simply going to be 0. So this motivates what's called smoothing. Smoothing is an incredibly simple idea. Whereas in a non-smooth language model, the theta I given j is given by the empirical probability of I being followed by token j. In smoothing, when you're counting and dividing, you add this lambda term that's typically between 0 and 1. And we can think of this as a pseudo count of how many times this event occurred. Now, this is a very simple smoothing scheme that might work well in practice, but many other smoothing schemes are possible.